This is the third in a series of resources on limits. We consider the basic idea of a limit and provide a formal mathematical definition for a limit. We look at three instances where a limit does not exist. We explore various properties that make finding limits simpler and look at multiple examples. We consider what it means for a function to be continuous, as it pertains to limits. We close the series by considering infinite limits. As the comic at the beginning indicates, sometimes finding a limit can be painful. However, there are numerous properties that make finding limits much more palatable. These first properties are trivial. To begin, assume that we have real numbers b and c and a positive integer n. The limit as x approaches c of a constant value b is equal to b. Since our function only takes a value of b, how could the limit be anything else? Another property is that the limit as x approaches c of x is equal to c. So the limit of a function that returns the value is the value. Makes sense. The final basic limit is that the limit as x approaches c of x raised to the power n is equal to c raised to the power n. So we can plug values in, so long as our function raises values to integral powers. Let's see some examples of these basic limits. Suppose we want to find the limit as x approaches 20 of the constant functions 55. Since the function equals 55 no matter what the x value is, the limit will equal 55. What about the limit as x approaches 20 of the function x? This function just returns whatever input we plug in, so the limit will equal 20. And the limit as x approaches 20 of the function x to the third power? We plug the 20 in for x and find the limit equals 8 thousandths. These limits have been very simple. How can we handle limits that are more involved? Luckily, there are a series of properties that allow us to simplify many limits. As before, assume we have real numbers b and c and positive integer n. Also assume we have functions f and g, where the limit as x approaches c for f of x equals L, and the limit as x approaches c for g of x equal to k. One property of limits is that the limit of a constant b multiplied by a function will equal that constant multiplied by the limit of the function. The other properties concern more than one function. The limit of f plus or minus g is equal to L plus or minus k. So the limit of two functions being added or subtracted is the same as the sum or difference of the limits of the functions by themselves. The limit of function f multiplied by function g is equal to L multiplied by k, or the limit of two functions multiplied by each other is equal to the limit of each function multiplied by each other. The limit of function f divided by function g is equal to L divided by k, so long as k does not equal 0. Descriptively, the limit of a division of functions is equal to the quotient of the limits of the individual functions. Let's look at an example. Suppose we want to find the limit as x approaches 5 of the polynomial function 3x squared minus 7x. We will use the properties of limits to simplify and ultimately solve this limit problem. First, we recognize that the polynomial is equal to the difference of two functions, 3x squared and 7x. We can separate the limit of the difference into the difference of the limits. We have the limit as x approaches 5 of 3x squared minus the limit as x approaches 5 of 7x. Next, we realize that we have constants multiplied by functions. We have 3 multiplied by x squared and 7 multiplied by x. These constants can be moved in front of the limits. We have the 3 multiplied by the limit as x approaches 5 of x squared minus 7 multiplied by the limit as x approaches 5 of x. Now we can actually take the limits. Plugging in 5 for x in each limit, we have 3 multiplied by 5 squared minus 7 multiplied by 5. Completing the calculations, the limit as x approaches 5 of the function 3x squared minus 7x is equal to 40. This example suggests additional properties for limits involving polynomial functions or rational functions. Suppose we have polynomial functions p of x and q of x. If we want to find the limit as x approaches some real value c, we merely need to substitute that value in for x and calculate. Suppose we have some rational function r of x defined by p of x divided by q of x. Then the limit as x approaches the real value c is equal to p of c divided by q of c. We find each function value, then divide. Let's look at an example. We want to find the limit as x approaches 2 of the quantity x cubed plus 3x squared minus 13x minus 15 divided by x plus 1. We recognize that this is a rational function. The numerator is one polynomial function that we will call p of x, and the denominator is another polynomial function that we will call q of x. When finding the limit, we just need to find p of 2, q of 2, and then divide the results. We plug 2 in for x in each function. Completing the calculations, we have negative 21 divided by 3. So the limit as x approaches 2 of the quantity x cubed plus 3x squared minus 13x minus 15 divided by x plus 1 is negative 7. One final property for limits involves composite functions. Suppose we have a composite function f of g of x. We know that the limit as x approaches some real number c for function g is equal to L, and that the limit as x approaches L for function f equals f of L. Then the limit as x approaches c for f of g of x is equal to f of L. Let's take a look at an example. Suppose we want to find the limit as x approaches 2 of the square root of the quantity 7x squared minus 3. We recognize this as a composition of functions. We have the square root, and we have the polynomial function underneath the radical. First, we will find the limit as x approaches 2 of the polynomial. Plugging in and solving, we find that the limit is equal to 25. Now we want to find the limit as x approaches 25 of the square root of x. Plugging in and solving, we have the limit equals 5. So the limit as x approaches 2 of the square root of the quantity 7x squared minus 3 is 5.